Hello, everybody. How's everybody doing? This is Rational Science directly from Frankfurt, Germany. Today we're going to talk about space-time, heaven and hell. Are you going to heaven or are you going to hell? Or are you going to space-time when you die? Well, whichever way you answer, it's wrong. See, because space-time, heaven, hell, is none of them are places. Okay? Like space-time, heaven and hell have to do with time. Okay? You know, when you're young, you're 15, 20 years old, you have all this vitality, all this energy, you run around, you have the strength, the stamina, you fall in love, you do stupid things because you don't have experience, you do unconscious things, then you repent, maybe. That's heaven. Okay, that's known as heaven. And at night you have the Sandman, and he comes around and he puts delicately, lovingly, little drops, little grains of sand in your eyes. You wake up in the morning, take the sand off, just brush it off, go to the fridge. You're hungry as a bear. You know that's known as that's heaven. Then at my age, yeah, the Sandman comes also, but he comes with a baseball bat and he beats you all night long. Wham, wham, wham. He just beats the hell out of you. And you wake up in the morning, oh, I got a stiff neck. Oh, my knee hurts. I think I have gout. That's known as hell. So heaven and hell is a question of time. You work your way from heaven all the way to hell. And we all end up in the same place, down there in the ground, okay? So, no, heaven and hell have to do with time, and so does space-time. Now, space-time is a synonym for the mathematicians, is a synonym of the universe, okay? That's what they mean when they talk about space-time. They talk about all of it. That's space-time, okay? But space-time has only been around maybe 100 years or so. Before then, we had other notions of what the universe is, okay? And one of the earliest notions of what the universe is, where we have solid evidence, right, is here, the Nebra Sky Disk. Okay, it looks like this. It was found approximately. It was made about 1600 years before Christ, and you can see there they show the sun, the moon. It's a little plate, about 12 inches, weighs about 5 pounds. Okay, so it's a great find. They found it in Germany. So this is one of the first notions we have of the universe that we can, put our hand on because it's a physical entity, okay? And, we progressed from there. We had, that was 1600 years before Christ. Now you're talking about maybe anywhere between 1500 to maybe 700 years before Christ. And you have most of the biblical verses and gives you an idea of what they were thinking about, as far as what the universe is concerned. This was some of their notions, okay? And if you read the Bible, you'll find it says, Then spake Joshua, and he said, Sun, stand thou still upon Gibeon, and thou moon in the valley of Ajalon. And the sun stood still, and the moon stayed. The sun stood still in the midst of the heaven, and hasted not to go down about a whole day. There was no day like that before it or after it. Oh, I'm sure. The day the sun stops moving, we're all in trouble, right? Hopefully there's no other day like that. Okay? And Chronicle says, The Lord made the heavens, the world also shall be stable, that it be not moved. That's where the flat earthers get the idea that the earth doesn't move, authority, and they also step every morning and they say, well, the earth doesn't seem to move underneath my feet. So between that experiment and authority, they figured out the earth does not move. Okay? And then you find a couple more references there, Isaiah. Behold, I will bring again the shadow of the degrees which is gone down in the sundial of Ahaz. You can see there the sundial on the bottom right, 10 degrees backward. So the sun returned 10 degrees, by which degrees it was gone down. In other words, the notion was that it was the sun that was going around the earth. Now, whether it went around the earth only in the sky or went under the earth and then over, that's up to you to figure out, or for a flat earther to tell you. They still believe in this stuff. And another one here, have ye not understood from the foundations of the earth? It is he that sitteth upon the circle of the earth. Okay, so what is the earth? Well, the Bible tells us it's a circle, and it doesn't move. And it's the sun that rolls around, and God commanded it to stop once and to go backwards also, 10 degrees. Okay, so those are more or less the notions they had in those days. They saw that little thing that they couldn't stare at, and they wondered what it was, and they said, well, you know, it's some kind of thing that rolls around the earth. And you know, even lots of religions turned the sun into a god. Almost, I think all of them did. You know, pretty much. They all thought the sun was a god of some kind. It gave them light. It gave them sunlight, and also they realized the crops grew thanks to the sun. So it was the sun who had to be worshipped for giving us a light to the plants. Okay, they knew that much at least. Okay, we went like that for centuries. When we reached the Greeks, maybe in their glorious days, anywhere from 500 to 200 years before Christ. Those were the golden age, you could say, of Greece. And you have this Aristotelian version, which is not his, by the way. It came before him. He just adopted it. And it's that you had these planets and the sun going around the earth. And you had the firmament, all these little lights stapled onto the firmament. And this was their notion of how the universe looked, okay? And one debate that happened in those days was whether the universe was infinite or finite. In fact, that debate has not stopped to this day. You have people out there talking about finite and infinite universes. And the question is, what are they referring to? You know, unless you define the word finite or infinite, you have no idea what they're talking about. Are we talking about the number of stars and planets and objects, celestial objects out there? Are those infinite, like counting is infinite? I'm not going to take the trouble to count them, so I'll call it infinite. Or are we talking about the extent of space? Space not having borders when we say infinite. What are we talking about here? Are we talking about space or the celestial objects? And unless that's clarified, when people say the universe is infinite or finite, we don't have any idea what they're talking about. Are they talking about the space component of the universe or the matter component of the universe? And that's the issue there. That was never resolved. It's still not resolved until this day. We still have, you know, relativists out there saying on the one hand that the universe had a starting point. Well, that's finite in one direction. And if it's still growing, still expanding, well, you would think it's pushing up against something. They deny it. They say, no, it's not pushing against anything. You don't need to push against anything. Well, yeah, that's only alluding to question. Because if it had an origin, it's a little ball or whatever, you have to imagine it is a almost perfectly round ball, the Big Bang or what came before then. Whatever came there exploded. They don't like the word explosion either, even though they call it the Big Bang. And it's still expanding, pushed by what? By the dark energy, right? Against the pull of gravity. Well, you're talking about a finite object. That's what they're talking about, a hand grenade that's exploding. Hopefully all hand grenades, I mean, if you film them through time, you know, at every frame of the film should show, you know, a border. And so it's a fair question to ask, well, what's outside of that border? Okay, so yeah, it's a question that's not answered, whether the universe is finite or infinite. They start out with a finite universe. We're still apparently in a finite universe, but then they talk about the infinite universe, like saying, you know, there's nothing outside of our universe giving it shape or turning it or containing it in any way, encapsulating it. So this is where the problem is, okay? And we haven't resolved that issue. Mathematical physics hasn't resolved that issue to this day. And they leave it like that and let everybody believe whatever they want. They say it's relative. Okay, not all Greeks believed in the geocentric universe. Some believe in the heliocentric universe. Here's Mr. Aristarchus of Samos, and apparently he's the first guy to propose it. Usually you find out there was someone before him, but this is the best we've got. We trace the heliocentric universe to him. Okay, so he said, at least he believed in it, and we don't have any of his writings, but people who wrote about him quoted him, and so that's where we get this information. And as you can see, you know, you have the sun at the center and the planets going around, the known planets at the time. Okay, so not everybody believed in the Aristotelian or Ptolemaic universe, and it's like it always happens. The majority of people believe in nonsense. It's always the case. It's been the case throughout history. The majority of people have it wrong almost always. Okay? But they believe in it, and they're the bosses because they rule. And a minority just hides in their caves and says, well, I know better, but I can't do anything about it. That's how humans work. Okay? So yeah, not very many people believed in the heliocentric universe. Certainly the Arabs rejected it. They rejected Aristotle when they read his writings, and they said, no, this guy's wrong. And that didn't really come into the Western world. Maybe it did, maybe it didn't, but it took many years to come, if anything, to come into the Western world. We had to sort of reinvent the wheel. And some people were aware of what the Arabs had discussed, whether that's what led to the heliocentric notion or model. It's your guess as much as anybody else's. You have different opinions on that. The point is that, yeah, eventually we came up with the heliocentric solar system. And time passed, we also discovered that there were galaxies out there. In fact, I think it was Immanuel Kant who came up with the notion of galaxy. He said those are island universes out there, okay? And the word spread, and so people started, seeing the universe in a different light. They realized it was maybe bigger than just the solar system. There was some other stuff out there. Galileo later on discovered some of the moons of Jupiter, and they said, oh my God, now we thought that it was only these few 7 objects here, the moon, the sun, and a few planets. They thought that was it. And now here we discover moons outside the Earth, outside our moon. And eventually, well, we discovered more moons all the way up to the 19th century. Okay? So, what notions did we have during this time? Well, we had this notion that, see if I can get it here, that, no, it's gone. Okay. We have this notion that until the 19th century, I would say, that the universe was this infinite, maybe, in the majority of people's minds, entity, space, whatever that was. They thought it was the ether because at least the ruling classes, the so-called intelligent or educated classes, they believed there was an ether pervading space, bunch of particles stretching all the way to whatever. They thought maybe it was infinite. And it was the vibration of that ether that formed light and other phenomena that they couldn't see. They probably couldn't figure out gravity, but they said, oh, but the ether is what is moving, what is waving when we talk about light. Okay? That lasted all the way to the end of the 19th century pretty much. And at the dawn of the 20th century, big changes came around, among them space-time. And I talked about this gentleman the other day. His name is Albert Einstein. He got his Nobel Prize in 1921, but he didn't get it for anything related to general relativity, to space-time. Even though at the time, not only did he have his equation, brand new equation which was introduced in 1915, and also we had around the same time the notion from Schwarzschild about the black holes. So we had these two whammies there, and nobody got a Nobel for that. All the way to the 1950s, no one got a Nobel in relativity. And that makes you wonder because, see, you have two pillars in mathematical physics. One is general relativity, the other one is quantum mechanics. Quantum mechanics received all kinds of prizes. I covered that the other day. You saw the prizes that these people got for dealing with particles and new particles and proposing theories about particles like Dirac's positive and negative C there, and matter and antimatter, that sort of thing. General relativity did not receive a single Nobel Prize in this whole time. It makes you wonder. Here we have two pillars, and one of the pillars is glorified. I don't know how many people really believed in it, but as far as I can see, you go all the way to 1920s at least, 1921, 22, a lot of mathematicians had bought into relativity. Not because of this gentleman, okay? Because remember, he's not the creator of special relativity as he's given even credit to today. Okay, here we have a gentleman I talked about a couple of weeks ago, and his name is Hendrik Lorentz, not the other fellow, not Zeeman, but Lorentz, and he's the guy who came up more or less, or one of the fellows who came up with a notion of special relativity, or the foundations for special relativity, which is, the time dilation. That's what these people came up with. Not only him, you have people like George Fitzgerald and Henri Poincaré, and Poincaré was French. The other fellow was, I can't remember if Irish or Scottish, one of the two. Anyways, some people will kill me. They'll say, don't you know Fitzgerald when you see one? Okay, whatever. And here Fitzgerald, together with another fellow, Oliver Heaviside, I'm not covering him, but All these people were involved with this issue of the time dilation. And we're talking about, 1889, 1892, 1889 when George Fitzgerald says, if all moving objects were foreshortened in the direction of their motion, it would account for the null results of the Michelson-Morley experiment. So here you had this null result, apparently, from Michelson-Morley's experiment saying, look, there is no ether. And Fitzgerald believed in the ether, so did Lawrence, and I think Poincaré as well. And all these people, they said, no, there is an ether out there. We just have to reinterpret the results of Michelson and Morley. And so they said, well, what if something squashed in the direction of travel? For example, the interferometer that Michelson and Morley used, So they were looking at it in mathematical terms, but they applied that to physics. They said, what if something squashed in the direction of travel? Then we would not notice, we would not be able to measure, the ether property. So that was one of the arguments, came from this fellow. And Poincaré, he added on to that a few years later. He said it was the first to present the Lorentz transformations in their modern symmetrical form. Okay? He discovered the remaining relativistic velocity transformations and recorded them in a letter to Hendrik Lorentz in 1905, year in which Einstein wrote his 4 papers, Annus Mirabilis, right? Thus he obtained perfect invariance of all of Maxwell's equations, an important step in the formulation of the theory of special relativity. Who formulated it? Poincaré and Lorentz. They did special relativity. Einstein, apparently gave it a different interpretation, and that's what he's glorified for. But the equations, the calculations, that was already in the books, and it was people like Poincaré and Lorentz who did that. Okay? And to this day, a lot of people don't even know them. They're certainly not given as much credit as Einstein, right? Okay? He's the guy, he's a celebrity, right? In 1905, Poincaré first proposed gravitational waves also. That's also given to Einstein, even though here you have Poincaré who talked about that earlier, okay, 1905. Okay, Einstein was 26 years old at the time working on other things, so he wasn't working on gravitational waves, okay, emanating from a body and propagating at the speed of light as being required by the Lorentz transformations. Okay. So you can see that Einstein got a lot of credit for stuff that other people did. I'm not saying that he didn't put his little grain of sand or that his interpretation was different or whatever. The point here is that, if they're going to glorify equations, here you have the equation guys. You have all these people like Heaviside and Lorentz and Poincaré and Fitzgerald. There were others as well. It's not like Einstein was the only physicist around. Okay. And again, there was no Nobel Prizes throughout almost the entire 20th century. Which makes you kind of wonder, well, what's going on? How come we have gazillions of prizes, Nobel Prizes, for the people who do quantum mechanics, inventing particles, theories also about particles, okay? All those got prizes. No one got prizes for general relativity, even for special relativity. And that should make you stop and think, okay? Anyways, maybe the first one, and I'm stretching my interpretation here, okay? First Nobel anywhere related to relativity is this fellow, Hans Bethe, a German guy who worked in the States. And what did he come up with? Well, he really wasn't into general relativity. What he did really was give an interpretation of how the sun works through fusion. And why am I putting that as relativity? Well, because he was trying to really explain how hydrogen came into being, okay? He says, look, hydrogen is not produced in the sun. We can produce anything above hydrogen, maybe above helium, but when you talk about hydrogen and helium, maybe helium, you can produce that in the sun as well, but when you talk about hydrogen, that can't be produced in the sun. So where did hydrogen come from? And that's when they took the clock back and they said, well, maybe it comes from the Big Bang, because at the time, this idea was floating around that maybe, just maybe there was an origin to the universe that came from Lemaitre and Hubble, who showed that the universe was exploding, okay? And they rewound the movie backwards and they say, well, if we rewind everything back, everything comes closer together, we end up with a little point, bingo. That's the start of the universe. That's a little ball where everything started and exploded and began to expand. And so Bethe was trying to show that hydrogen had to be created at the Big Bang. Okay, so this is why I'm putting him in here. But he gets his prize in 1967, and not really for Big Bang, but it's like, veiled a little bit and saying, well, he got it for showing that, how a star works. Okay, and I'm not going to trivialize that because, I think it's a pretty good job. It's just that, what does it have to do with relativity? And that's what they were trying to do. They were trying to explain the origin of the universe, actually the origin of hydrogen. Okay? They said, how did hydrogen come into being? How did protons and electrons come into being? They went to the Big Bang because they said only at the energy that we can imagine was present at the Big Bang, that's the only way you can justify the creation of protons, electrons, and eventually, atoms such as hydrogen atom. Okay, next fellows to win a Nobel for something related to general relativity were these two fellows. Okay, they had to split the medal. In fact, a quarter of a medal each because the main half went to someone else for a different reason. For what did they get it? Well, they got it for their discovery of the cosmic microwave background radiation, Penzias and Wilson. And the funny thing about this is, like I said the other day, they bumped into an elephant and they said, oh, we discovered an elephant. And they got a Nobel for that. It's not like they really thought about something like, I say, you see the magician on stage and you try to figure out how he did the trick and then you figure it out and you say, I discovered how he did the trick. Okay? That's good because you broke your head. These guys didn't break their heads. They just bumped into the wall and they said, oh, we discovered the wall. They discovered the CMBRs in some cases, accidentally. And it was another group that told them, hey, you discovered what we needed, what we were looking for, and that was the cosmic background radiation, the remnant, alleged remnant of the Big Bang, of the moment of the explosion, of the initial explosion, without God. There was no God there, okay? They got rid of God. They said it happened all by itself. And so they got the prize for that, for saying, okay, so they discovered the background radiation, about 3 degrees Kelvin out there of some weird noise or vibration. And together with other people, they eventually were able to convince the community that that was, the remnant of the explosion of the Big Bang. And of course, since that reinforced the Big Bang theory, these guys were heroes. Okay? He said, hey, you discovered something great. You discovered a oil well or a pot of gold at the end of the rainbow. Next fellow who got it, he got it a little late. Maybe this guy should have gotten his a lot earlier, and he would have broken this notion, the record, and received a Nobel Prize for relativity in the first 50 years, because he did his work in the 1930s. But nobody believed him. That was a problem. And until they believed the relativity, or at least what he discovered, which is black holes, okay, he lost it. Hold on. Until they proved the existence of black holes, they weren't about to give him a Nobel Prize. That was the whole issue. And it's this guy, Chandrasekhar, Indian fellow. And the guy on the right, not important at all. Nobody knows him anyways, but he got the other half of the medal for something similar. Okay, I think it was for radiation. But it's Chandrasekhar, the guy we're interested in here, because he's related to the black hole. He's the guy who proved, not what they say there, he showed that when hydrogen fuel of stars of a certain size begins to run out, it collapses into a compact, brilliant star known as a white dwarf. Okay, maybe he got it for that as well, but he's known for something totally different, and that's why they really gave him the prize, or why they considered him for the prize. And it was the fact that he proved that a black hole collapses to zero size. And a lot of people today don't understand that. They don't know or are not aware that there's a Nobel Prize for showing that black holes collapse to zero size. That's what his work was all about. He was overruled by his boss, Arthur Eddington at the time, his supervisor, and he felt bad about that. But he kept publishing, and other people kept publishing, among them Oppenheimer, who would run the atomic bomb program. And others that came afterwards. In fact, in the 60s, you have Penrose and Stephen Hawking. And they were the guys who kind of popularized the black hole. And that's when this guy came back into the limelight, and they said, okay, give him a Nobel Prize. What the hell, out of pity. And so that's how he was recognized, Chandrasekhar. Okay? But he's really known for the black hole, not for white dwarfs. Okay? You look it up, you'll find that it's all about black holes in his case. Okay, who came next in the lineup for Nobel Prizes related to relativity, okay? It's these two fellows. And again, they shared half a medal each, okay? Not great when they give you only half a medal. for the discovery of a new type of pulsar. Okay, so they discover a pulsar, but that's not really what got everybody excited. It was something else, that Hulse Taylor could demonstrate that a pulsar would emit energy in the form of what? Gravitational waves. Discovered by whom? By Poincaré? No, by Einstein, remember. Give credit where credit is due, okay? Einstein discovered gravity waves, and now these guys prove them, so we're done. You know, it confirms general relativity, confirms space-time, and it confirms gravity waves, which even Einstein had abandoned, but these guys kind of resuscitated and said, no, Einstein, you were right. Okay, even though he was shown by mathematicians in the in the late 1918, 1919s, but for certain by the 1920s, they showed him that he had made errors in his calculation. He accepted the errors, and then these guys resuscitated, many years later. Okay, so they proved the existence of gravitational waves. Obviously, there were more people proving gravitational waves, as we saw a few years ago. Okay, and here's the next group. Not important, so I didn't include them in any special way. Okay, one pioneered cosmic X-ray sources. Think about that as black holes or some other X-ray source, cosmic object, right? That emits X-rays, so he gets a Nobel for that, half a Nobel. Okay, that was in 2002, and then these guys, I didn't put the date there. It was 2006. For the discovery of the black body form and anisotropy of the cosmic microwave background radiation. Again, the CMB, they had to prove that at all costs because a lot of jobs depended on it. A lot of people studying black holes and also Big Bang. And they had to find proof, evidence, and this is what these people provided. They say, oh, we have proof. We have proof for the cosmic background radiation, and here's more proof, and here's more proof. So it was all about this cosmic background radiation that they measured, and they were able to prove its existence in different ways. And it's the physical interpretation that we're concerned about here. That there's something out there buzzing, 3 degrees Kelvin. Okay, fine, no problem. The question is, what is it? And it's the interpretation that they say that's the remnant of the Big Bang that is the issue. Okay? Because then they have to explain the Big Bang, and that's when they stop at frame number 2 of the Universal movie. They never go to frame number 1 because they claim they don't know what happened at frame number 1 or even before then, and it's an unscientific question because they have no way of testing that theory or hypothesis, whatever they call it in mathematical physics. Okay, so this was the issue. Okay, next came another fellow. His name is Perlmutter, and a couple others. That shared only a quarter of a metal. And you can see why that guy on the bottom, Adam Rees, he doesn't look very happy. And I don't think I would too. I mean, if I only receive a quarter of a metal, I spent all my trip, my time, and my money to get to Sweden just to get that. I mean, it's not fair, Anyway, so what did these fellows discover? Well, let's see if I can get it up here. They discovered the, where is it? The expansion of the universe, okay, and known as the dark energy, okay. So you can see there the little ghost, okay. For the discovery of the accelerating expansion of the universe through observations of distant supernova. Okay, so what did they do with this? Well, they confirmed, let me get this fellow out of there. They confirmed once again that Big Bang is a reality, that there was an explosion. Today we say it's 13.8 billion years ago, Earth years, and it's still expanding. Everything's flying away from each other. And what's pushing it away is this dark energy. And you say, what do you mean pushing it away? Well, see, this is the problem. The problem is the theory, and the theory is that gravity pulls everything in. And so like Newton addressed this issue already in his time, if everything's being pulled in, why doesn't the whole universe collapse into a single ball? And so these folks said, we'll tell you why, because there's this explosion that happened a long time ago. They said, well, it should have lost steam by now. It should have reached a point where now it's drawn back by gravity. So what keeps it going? And that's when they had to invent dark energy, which they claim is like 70+% of the universe, an unknown substance. They don't know what it is. It's just put in by hand. And they said, we need to put that by hand to show the expansion of the universe against gravity, because otherwise gravity would pull everything in. That's the theory. That's what it's all about today. So this is the situation. The situation is you have to counteract gravity. And that's what they invented dark energy for. And they said there's got to be lots of it because to overcome gravity, you have to have lots of this stuff. But we can't see it. We don't know what it is. So we'll call it dark energy. And now it's a variable that they use in their equations, and they're happy with it because they have this number called dark energy. They don't know what it is. They tell their astronomers, go look for it. It's invisible, intangible, but go look for it. That's where we're at. That's where we're at. Okay, who came next? Oh my God, I keep sending it to the other side. It's these fellas, and oh my God, did it again. There we go. New mouse. So I keep sending it to the bottom instead of the top. Okay, I covered these guys in the past, okay, especially the guy in the bottom, Kip Thorne. Okay, and what these guys did, they had this LIGO, okay, collaboration. They had to show that LIGO was useful for something. And what they proved with this, again, was the existence of gravitational waves. For the 10th time, again, they proved them. Okay, so we keep proving the same thing over and over, just confirming, through experiments, just to double check and triple check to make sure that we covered all the bases. And what they proved is gravitational waves. How did they prove them? Well, they said there was a collision of two black holes somewhere out there in the middle of nowhere. And we received the waves from that collision. Okay, similar to what you just saw for the pulsars. Okay, no different than that. And finally, we get these people, also cover them the other day, and that's especially Mr. Penrose there. He's been around for at least, I would say, 60 years. They had to give him a Nobel before he died. They would have given one to, to Stephen Hawking also, but he decided to leave us and go to heaven or to hell. I'm sorry, it was hell, the space-time, right? And so Penrose received a medal together with these two other folks who received like a quarter medal each. And again, for proving the existence of black holes. Okay, that's what their work was all this time. One theorized about them, the other guys supposedly proved their existence. How did they prove them? As Gensel himself says in his paper, he proves it indirectly. What else could it be? That's his entire reasoning. Okay, he cannot think of any other possibility what could cause those effects, and I showed that there is another possibility. But today we're talking about universe, and so what do we end up with? What's the relativistic universe after all these decades, this century that's gone by? What does the universe look like? Does it look anywhere like Aristotle or any of these other folk? Well, here you have several versions of the universe, of this space-time thingy. Okay, you have one which shows that it collapses into the earth, because you have to show why something would fall to the center of the earth. So you have to make this three-dimensional fishnet move inwards, like it's pulling things inwards. So they say, well, you fall towards the center of the earth. Well, then you have the two-dimensional version, which is where the earth weighs down the canvas and things fall into the hole of the canvas. These two are totally different mechanisms, totally different notions of how our universe works. And they're all accepted. Nobody complains about them. The mathematicians don't care because they don't care about physical interpretations. They just care about their math. And they say, we got the math, we're covered. We get Nobels. And then let the plebes, the ignorant people out there, the peasants, they come up with all this stuff. They say, well, here's the universe. And a lot of the second one there, comes from high-level people, but this is what they feed the public. Okay? And the other one is believed by a lot of people as well, so it doesn't matter. Okay? This is out there and people don't know what to believe because the scientists, so-called scientists, the mathematical physicists, can't tell them and won't tell them what the universe looks like. Whether it's infinite or finite, whether there is a space-time that bends when the Earth sits on it, or it bends into the Earth, which is the one on the top. Okay, so they can't tell you that, and they won't tell you that because they don't have an answer. They say, well, you have to imagine as an analogy, blah, blah, blah. And you say, okay, is that how the universe runs? And they say, it's just an analogy. Don't take it so seriously. In other words, they don't know. They give you an analogy and then they take it back saying, well, it was just an analogy, whatever that means. Okay, I need a mechanism, how the universe works, why the Earth doesn't fly out of the solar system, or why the moon doesn't fly, out of the Earth orbit. Is it a depression that's preventing? Is there a wall of time, curved wall of time around the Earth, and that's what the moon is rolling around? Is that the wall that prevents the moon from flying out? Is that the analogy? This is the issue. The issue is they don't have an explanation. Today here, with all the math, we don't have a notion of what the universe looks like. And again, whether it's infinite or finite, we have no idea. Not from the mathematical physics world. Now, from our world, yeah, we do have, here's our version, okay, side by side. Okay, all the galaxies in the universe are interconnected physically, and probably the entire universe is rotating, okay, in some way, maybe in different directions. I have it here going in the same direction, okay. But that's what our universe looks like if you had, I guess, the eyes of God and you were looking at it from afar, okay. So that's the notion, a little different than the one they propose, okay, of bending space-time and four-dimensional, unimaginable space-time. We don't have that. Okay, that's mathematical physics. Big word there. Okay, and here's another version. Okay, I'm saying it's just a single thread out there, and this thread is what converts into all the atoms and ropes that interconnect them. And that's how simple our universe is. It's no more complicated than that. Now, of course, because the thread, the rope, is invisible and intangible, and I'll prove it to you. Okay, here's a pencil. Okay. I'm touching nothing here other than air, okay? I don't see anything. Hopefully you don't see anything either. And I let go of the pen and it falls to the floor. So yeah, gravity is intangible and invisible. Whatever mediator is between the earth and the pen is invisible and intangible. So it's irrational to go to the lab, like some people ask me to do, and say, show me in the lab that there are ropes and there are threads. I can't show you because I can show you a thread, a sewing thread, and this is a thread. And here's a rope, okay? Okay, you know what a rope looks like? Like that, 2 twine threads. Okay, that's it. And he said, well, show me in the lab that this works. Well, I can show you the mechanism of, maybe tie a whole bunch of ropes and show that it'll fall to the ground, but it'll be gravity from Mother Nature's gravity that pulls it down. It's not going to be the ropes. But I can show you I can pull with a rope, okay? But whatever I do, I can't show you that rope with which I pulled on the basketball or whatever I do the experiment with is intangible and invisible. Every object in our macro world is visible and tangible. Most of them are. Air is not, And again, why is the rope invisible and intangible? Well, because you can only see it through aggregation, okay? You can't see one atom, but you can see the chair, you can see the table, which is made out of atoms. But you cannot see individual atoms. And so because of that, the atom is not there, the table is not made of atoms, the chair is not made of atoms. What is the chair made of? Ghosts? Is it made out of concepts? Hopefully the chair is made out of some physical object. We call that physical object an atom, and we can't see an atom. We can't really touch an atom. You touch it like when you touch the chair, but one single atom, hydrogen atom, well, I don't know if you can show me the test that you really touched an atom, okay? And similarly, the only way you can see the rope is when it bunches up. Okay, and how does it bunch up? Well, it bunches up in something called an atom. The rope forks out, turns into these threads that go around the atom and form this ball with the star in the center. And now you can see not one atom, but many atoms together, which we call chair, elephant, tree, rock, whatever. So yeah, you can only see the rope when it bunches up, when you have many of them in some form. And again, the thread is the same thing. You can't see the thread, but when the thread acts in magnetism, forms these walls that sweep around, then it causes an effect. You can't see it, but it causes an effect, much like air. You can't see the air, but it causes an effect. You have a lot of air, it blows your house away. Okay, so yeah, air is that invisible thing that blew your house away. And the threads are what form the magnetic field that goes around a magnet, and it picks up iron filings one after the other underwater. Okay? So yeah, we have a different universe than the one general relativity ended up with after many Nobels. And I'm sure the people from 19th century backwards, all the way to Aristotle and beyond, they would be appalled what mathematical physics finally led to.